All right, here we go into the calculus of the natural log. It's going to be awesome. And actually, the process of it is very, very simple. So that's what I'm going to start out with in this video. We're going to go over just procedurally how to take the derivative of ln of something. How do we deal with that? And then at the end of the video, I'm going to go over why the derivative makes sense. So without any further ado, here it is. The derivative with respect to x of the natural log of x is 1 over x. That's it. It's 1 over x. And so what happens when we've got a function within a function? So let's say u is some function of x, like u is f of x. So how do we deal with that? Well, that would be 1 over that u times du dx, or u prime. So a lot of people write that as u prime over u. I've also seen written as 1 over u times du dx. Either way, it's the chain rule. That's what that is. That's all that is. You've done the derivative of the inside before, right? The outer function's ln, so it's 1 over stuff, d stuff. And that's how I like to think of it. You got ln of stuff, 1 over stuff, times d stuff. All right, well, that'd be the derivative of stuff. That's your chain rule. It's very informal. Let's do it. Let's see how easy and quick this can be. Shall we? We shall. So this is y equals the ln of x minus 5. The derivative of that, well, in my mind, up here, I'm looking at that and saying this is the ln of stuff. So that would be 1 over all of that stuff. So dy dx is equal to 1 over all that stuff times 1. You don't actually have to write that, but that's what's happening there, because the derivative of x minus 5 is just 1. So it's 1 over x minus 5. How about letter B? Well, what's f prime of x? That's what we're looking for. It says find the derivative of each. So that would be all of this is the stuff, group it all together. That's equal to 1 over stuff. So 1 over 3x squared plus 5 times the derivative of that inner function, which is 6x. That's it. And so we can rewrite that as 6x over 3x squared plus 5. Isn't that beautiful? So simple, so straightforward. All right, what happens when we've got a product? Oh no, no sweat, we can deal. This is a product rule. We've got a first d second plus a second d first. When you get to the ln part, then invoke or use your ln rules. So the derivative, y prime, is equal to the first function, that's this, right here, times the derivative of the second function. It's ln. The derivative of ln of stuff is 1 over stuff, d stuff, which is just 1 in this case. So that's first d second plus second times the derivative of the first. Now, we'll just kind of condense this and we'll be on our merry way. Y prime is equal to, the x's divide out, you're left with 2, plus, be careful here, this is not ln of x times 2. Like the 2 doesn't end up in the argument of the log. You're not taking the log of 2 and x. So that would be plus 2 ln x. There you have it. There's your answer. All right, we've got a couple more. Oftentimes you're going to see things with absolute values. Ooh, no sweat. You got this. When there's an absolute value involved, you ignore it. It literally does not play a role at all. And there's certainly a wicked fun math proof on this, but to the majority of the people watching these videos, let's be honest, most of you are probably like, yeah, I don't really care to see the proof. I'm jumping out of my skin to show you the proof, but I'm not going to do it here. If you end up having a question about that, reach out to me. Be like, yo, G-Dog. Apparently that's my name now. Please show me the proof of why the absolute value of, with an ln function ends up being the same thing. So ignore the absolute values essentially. This ends up being 1 over stuff, the stuff being sine of x, times the derivative of stuff, which is derivative of cosine, or derivative of sine is, there you go, cosine. And that simplifies to being cosine over sine x. And some of you will be like, well, Groden, can't you just write that as cotan? Certainly. Certainly you may. Any of those are fine. 1 over stuff, d stuff. All right, last one, and then we'll get into the why behind all of this. Oh no! We've got ourselves a quotient, ln of stuff over x squared. No sweat. Do the quotient rule, and when you get to ln, your brain should just focus on the ln rule, and then we'll go back out to the quotient rule. We've got bottom d top. So that's going to be, well, f prime of x, let's write that out first, of course, notation first. Bottom, x squared, d top. Okay, this is where our brain now goes to ln. It's 1 over stuff. 1 over x squared. Oh, sorry, it's x cubed. X cubed. 1 over stuff, d stuff. What's the derivative of that? The derivative of this is 3x squared. Ah, so bottom d top, come back out now, look at your quotient rule. We did that, used our ln rule. Bottom d top minus top ln of x squared plus 3. Ooh, this is a right mess, isn't it? So bottom d top minus top d bottom. Ooh. All over the bottom squared. That's x squared squared. So I'll write that out. Okay, we got a little bit of cleaning up to do here, but it's not bad. X squared times x squared is 3x to the 4th. All over x cubed plus 3. That's just this component right here. This, remember, it's not 2x times what's in the log, it's 2x times the log. So minus 2x ln times x squared plus 3. Very nice. All over x to the 4th. Now, some teachers are fine with you leaving it like that. Others are going to be like, yo, if you're dividing everything by x to the 4th, take that x to the 4th and just put it underneath each fraction, right? Because you're dividing this by x to the 4th, you're dividing that by x to the 4th. And that's going to lead to some nicer simplifying. So just want to put that there in case you have one of those teachers who are like, yo, got to simplify further. This is how you do it, and you got a little bit more that we can write. The x to the 4ths divide out. You're going to be left with 3 over x cubed plus 3 minus 2. And this is going to be ln of x squared plus 3. And then you have x cubed in the denominator. We got that because they divided out. By the way, in the A, B, or BC exam, if all you're asked for is the derivative and it's a free response problem, that's good enough right there, seriously. Okay, so last but not least, why does the derivative of ln of x make sense? So if you're like, nah, I got it, the process is easy, that's all I need for class, then you can stop watching. But come on, don't you want to know why? It's pretty cool. So what I have here is the original graph of ln x in orange. And then in this other color, I don't know if it's light blue or purple, I'm colorblind. If you didn't know that about me, I am. You've got 1 over x, which is the derivative. So here's y, and here's y prime. Now, remember that the y values on the derivative are the slopes on ln x. Let's take a look at the slopes of ln x just briefly. They start out very, very positive, and then they get less positive. The y values start out very, very positive. And as we go, the y values get significantly less positive. But the entire time, we've got positive slopes. The slopes are getting less and less, and they're approaching 0, but they'll never quite get to 0. And the y values are getting less and less on the derivative, but never quite approaching 0, always staying positive. Now, if you want to go even deeper, the slope of the derivative function is negative the whole time, and the slope of the derivative would be the second derivative. So if the slope of the first derivative is always negative, the second derivative is always negative, y is always concave down, and sure enough it is. All right, I just wanted to show you that just so you could be like, oh, okay, I see why these things connect. It makes conceptual sense. Now there's a proof of the derivative of ln x being 1 over x, and it involves the difference quotient from way back in chapter 1. I'm not going to go through with that right now. I actually think that there's a lot more merit to going over the concept graphically. All right, I'll see you in the next video. We'll do more with the derivatives of ln. Can't wait. Peace.